All right, the last time we were together, we talked about fission, which is one way to trigger a nuclear reaction. Today, we're going to talk about really the opposite type of process, which is fusion. Fission is when I take a large particle and I bombard it and I split it into two smaller particles. Fusion is when you take smaller nuclei and you combine them together to make a more massive nucleus. Now, fusion requires, in order for it to be able to take place, it requires huge amounts of pressure and a very high temperature in order for these reactions to happen, okay? So this is not something that's going to take place unless the conditions are very, very favorable for that. So as an example, fusion is exactly the kind of process that happens in the sun, and it's what enables our life here on Earth to keep going, because we have the heat and the energy from the sun to warm us and to provide the light that we need. So if this happens in the sun, what the equation looks like for the fusion reaction that happens in the sun is this. We take 4 hydrogen atoms, just very simple hydrogen atoms, and we fuse them together, and what that does is it makes a helium atom, and it makes a couple of what are called positrons. Now you'll notice that looks very much like the electrons that we were using in beta decay. The difference though is that while it looks like an electron in every other aspect as far as the mass of it, remember electrons are much smaller than protons, these do not have the negative charge associated with them. Instead they have a positive charge, hence they're called positrons. All right, so here I've taken 4 small nuclei and I fuse them together to make a large nucleus instead. Now, what is true about fusion is that this makes 3 to 4 times as much energy as fission does. And so you may be thinking, well, if that's true, then why don't we use fission reactions in place of fusion reactions? Or why don't we use fusion reactions in place of fission reactions? I said it backwards, sorry about that. In order to produce our power, if it's going to produce that much more energy. Because for one thing, this doesn't have, it produces very few harmful byproducts. Well, the problem is that with the huge amounts of pressure and the very high temperatures that it's required, it takes so much energy to get these reactions to occur that with what scientists have been able to discover so far, it just simply isn't cost effective. To get those high temperatures, you've got to obviously have a great amount of heat being produced someplace to produce the high pressure. You've got to have something that's going to produce that pressure, which is going to take energy. And so scientists are still working on ways to try to make it possible for us to get our power from fusion reactions in place of fission reactions, but we're not there yet. So the other question that comes up that may have occurred to you is, well, where does all this energy come from? Because energy isn't something that we really see when we write the reactions in this way. What is true here is that in all of these nuclear reactions, the total mass of the products is less than the total mass of the reactants. Let me actually write that down so that you can see that. So the total mass of the reactants, so what you start with, is greater than the total mass of the products. And now you're probably going, hang on just a second there, Mrs. Thompson, because we talked about the law of conservation of mass. You said that we can't create or destroy mass. That's true. We can't create it, we can't destroy it, but we can change its form. And you may have seen the equation before, E equals mc squared. You see that a lot of times in conjunction with Einstein, who developed the theory of relativity. Well, basically what this equation tells us is that mass, which is what this m stands for, and energy, which is what the E stands for, mass and energy are interconvertible to each other. I can take mass and turn it into energy. And so C, in case you were curious, stands for the speed of light. So we're not going to be using this equation in this class, but this equation does tell us that I can take some of the mass that was present in these atoms and I can convert it into energy. And so therefore, it is possible for the total mass that I start with to be greater than what I end up with, because I am taking that mass and converting it into energy, and then that's how I can power my nuclear power plants. All right, so one other thing that I want to mention briefly is that a lot of people, when they hear the word radioactivity and nuclear power, they get really scared. And they think, oh, we're all going to die of radiation poisoning. And certainly when you have incidents like happened at Chernobyl, when you have nuclear power plants like the one in Japan recently where the tsunami hit it, and then you start having meltdowns because those reactions get out of control because of these other things that happen. Yes, radioactivity can be dangerous, but for the vast majority of us in the vast majority of places, we can harness radioactivity to use it for our benefit. And in reality, we're all exposed to radioactivity every day, and even living near a nuclear power plant doesn't provide as much radiation as you might think it does. And so the very last lab that you're going to be doing in this chapter is going to really kind of show you how much radioactivity each one of us is exposed to every day and how dangerous is it really. So I hope you enjoy doing that lab. I hope you learn something from it. And that is going to complete then our chapter on nuclear change.